My name is Melissa Reyes, and today we will talk about what they taught us in chemistry for our final exam. So, we're going to start with the concepts of matter. Matter is anything that has mass and takes up space. Matter is made up of atoms and at least one subatomic particle. A pure substance is another term for matter. A pure substance only has one type of molecule, atom, or compound, and cannot be broken into two or more simple substances by physical or chemical change. Some examples of a pure substance are table salt and baking soda. A mixture is a combination of two or more pure substances in which they cannot retain their own properties. Examples of a mixture are salt and sand, and as well mixing water with sugar. If you were to dissolve this water, then all the sugar particles will be all crystallized at the bottom, so this is a reason for why it's a mixture. There are four main states of matter, which are solids, liquids, gases, and plasma. A solid has a definite shape and volume since its molecules are compacted very tightly together and move very slowly. Examples of solids are wood, rock, and sand. Then there are liquids, which has a definite volume but no definite shape. Liquid molecules are not as quite compacted and they move a little bit faster than solid molecules. Examples of liquids are water and oil. Then there is gas, which does not have a definite volume or shape. Here its particles are widely spread and move freely. Such gases are the oxygen we breathe, which is everywhere around us, and helium inside of balloons. Lastly, we have plasma, which does not have a definite shape or volume. It's not bound to ions and it is electrically conductive. Examples of things that contain plasma are the stars in the sky and neon signs. Physical properties. A physical property is something that can be observed or measured without changing the state of the substance. Two forms of physical properties are intensive properties and extensive properties. And intensive properties are properties that do not depend on the amount of matter in an object, which include melting point and boiling point and density. Then there are extensive properties, which do not depend on the amount of matter in an object. Such examples are mass, how something weighs, and volume. Physical change. A physical change is a change from one state to another without changing its chemical composition. No chemical reaction took place. Such examples of physical change are boiling point and melting point. Lastly, we have chemical change. A chemical change is when a substance's chemical composition is changed into a different substance. Some examples are burning a candle and even making tamales, because this bitch isn't going back to how it was. It's gonna stay a tamale unless I eat it. So now that we talked about the fundamental concepts of matter, I will give a brief history about the periodic table. In 1789, Anthony Lavoisier classified substances into metals and nonmetals. In 1829, de Bruyne divided elements into groups of three elements with similar chemical properties known as de Bruyne's triads. In 1869, Dmitry Mendeleev started the development of the periodic table, arranging chemical elements by atomic mass. So this is Dmitry Mendeleev. In 1914, Morse rearranged the elements in order of increasing proton numbers in the periodic table. Periodic trends. A periodic trend is attributed to atomic structure of each element. Periodic trends consist of electronegatividity, ionization energy, atomic radius, electron affinity, ionization energy, and nonmetallic and metallic character. Atomic radius. The atomic radius of atoms decrease from left to right across the periodic table. The atomic radius is generally stated as being the total distance from an atom's nucleus to the outermost orbital of electrons. Wait, I'm trying to oh well, I lost. So, as you can see here, the atomic radius increases as it goes from right to left, and by this you can tell that it will decrease if it goes from left to right. Ionization energy trends. The ionization energy increases as we move from left to right across the periodic table, and this makes the atom more attracted to the nucleus. As the ionization increases, the number of protons and electrons in an atom increase as well. The higher the ionization energy, the more difficult it is to move an electron. It helps predict the strength of chemical bonds. Moving left to right across the periodic table, the atomic radius decreases. Moving down a group of valence is added. The outermost electrons are further from positive charged nucleus. So for ionization energy, as tell here, you can tell that from left to right it increases, and from right to left it will decrease. Electron affinity. Electron affinity reflects the ability of an atom to accept an electron. Electron affinity decreases down a group of elements since each atom is larger than the atom above it. Electron affinity is a quantitative measurement of the energy change that occurs when an electron is added to a neutral gas atom. The more negative the electron affinity value, the higher an atom's affinity for electrons. Electronegativity. It is a chemical property describing an atom's ability to attract and bind with electrons. Most atoms have 8 electrons because elements on the left side of the periodic table have less than the full valence shell. The energy required to gain electrons is higher. The nature of electronegativity is described as the more inclined an atom is to gain electrons, the more likely the atom will pull electrons towards itself. So basically, if such elements only have 7 outer electrons, it will try to keep on attracting more elements so it could have more electrons until it has 8. From right across the periodic table, elements' electronegativity increases. From top to bottom down a group, electronegativity decreases. So there isn't really electronegativity. Bonding. So there are 3 main types of bonding: ionic bonding, covalent bonding, and intermolecular and metallic bonding. Ionic bonding is when a positive charged ion forms a bond with a negative charged ion, and the atom transfers electrons to the other. An example of ionic bonding is sodium chloride. So as you can tell here, the sodium is positively charged and the chloride is negatively charged. Since it has one valence electron outside, it will transfer it towards the chlorine. Since when it has a positive charge, it takes away electrons, and when it's negatively charged, it gains electrons. Covalent bonding is when pairs of electrons are shared by atoms. Covalent bonds form between 2 nonmetals. An example of covalent bonding is water. Metallic bonding is a sharing of many detached electrons between positive ions, where the electrons act as glue, giving the substance a definite shape. Everyone puts their efforts together to make something happen. It is responsible for high conductivity, reflective malleability, and ductility of metals. Such examples of metallic bonds are just like the wires that we use to take our electricity around our homes. Intermolecular forces are what determine properties such as melting point of solids and boiling point of liquids. The three major intermolecular forces are dispersion force, dipole-dipole interaction, and ion-dipole interaction. So, dispersion forces are often found in halogens such as carbon dioxide and methane. They are a type of force acting between atoms and molecules. Dipole-dipole interactions are attractive forces between polar moles. Such examples of this is, as you can see here, in molecule A, it has a negative S pole and a positive S pole, but the positive S pole is bigger, and then there's molecule B, which has a negative S pole and a positive S pole. The positive S pole will be attracted to the negative S pole of molecule B. Ion-dipole interactions is the force between an ion and polar molecule. Such examples is when sodium chloride dissolves in water. The reason for this is it dissolves is because the polar water molecule attracts ions more than the ions attract each other. So here you can tell that in sodium chloride, it changed its substance since the hydrogen got attracted to the O and water, and yeah. Okay. So, transition metals are a group of metals that are found in the I of the periodic table. Transition metals act as a bridge between highly metallic alkaline metals and alkaline earths on the left side of the periodic table, and non-metallic nonmetals, which are halogens and noble gases, on the right side of the periodic table. So, as you can tell here on the left side, on the left side here, the alkaline metals and the alkaline earth metals, it is separated by the transition metals. I'm not sure if you could tell. And then here's the halogens and the noble gases, which are separated as well by transition metals. So common ions consist of cations and anions. Cations are positive charged and anions are negatively charged. Such examples of these are sodium and iodide, which gives us sodium iodide. The formula for this is cation plus anion plus the ID, the prefix ID, which equals a compound. So here we have sodium, which is the cation. Then we have iodine, which is the anion, and then we have the prefix "ine", which gives us sodium iodide. You just need to change the ending of iodine to "ide", and it gives us sodium iodide. Now we will get into atomic and nuclear chemistry. Protons are subatomic particles with a positive electric charge. They are located inside the nucleus. Its role is to help bind the nucleus together. They also attract negatively charged electrons and keep them in orbit around the nucleus. Then there are neutrons, which are subatomic particles found inside the nucleus of an atom. It has no electric charge. It is neutral. Its role is to add mass to the atom, provide stability to the atom, and prevent protons from repelling one another. Lastly, we have electrons, which are negatively subatomic particles located in the shells or orbitals that surround the nucleus of the atom. Its role is to maintain the atom neutral, and they share in between atoms to make covalent bonds. So here in this little chart I drew, here are the protons, which are positively charged. Then here are the neutrons, which are negatively charged, and then the electrons, which are outside in the valence shells. Okay, so you can calculate protons by having a periodic table, which like the one I have here, and if you can see the atomic number at the top of the element symbol, then then and that's the atomic number. And the element is equal to a number of protons. To calculate neutrons, subtract the atomic mass of the element by the atomic number. Lastly, to calculate electrons, it is the same as the number of protons the element has. History of atomic nucleus. In 1911, Rutherford discovered atomic nucleus in which every atom contains a nucleus where all of its positive charge are concentrated. He discovered this through his Geiger Marsden gold foil experiment. Nuclear radiation is particles and photons emitted during reactions that involve the nucleus of an atom. Nuclear radiation can lead to radioactivity decay, which happens when an unstable atomic nucleus loses energy by radiation, such as an alpha or beta particle. The nucleic emits radiation to be able to become more stable. Alpha decay contains two protons and two neutrons plus energy. An alpha particle, the nucleus loses two protons, which changes the atom into a different element. Then there is beta decay, which contains one electron plus energy. For each beta particle and beta decay, the nucleus either loses or gains a proton, which as well changes the atom into another element. Lastly, there is gamma decay. The number of protons remain the same. Gamma decay usually occurs after alpha or beta decay. It occurs when the nucleus is is in an excited state and has too much energy to be stable. Half-life is the time it takes for one half of the element to disintegrate. The formula for half-life is here, which is A equals N0 times 1/2 over T, then there's TH. So then the A is the final amount, the N is the initial amount, and then the 1/2 is the split factor. After half-life, 1 pound becomes 1/2. And then the T represents the time and the H is the half-life. So now we go to electron configuration is a standard notation used to describe the electron structure of an atom. To find the electron configuration of an element, find the atom's atomic number, then use the electron configuration chart, which is this one. So for our electron configuration, let's find the electron configuration of one element. And we will use, let's go a short one, lithium. Lithium's atomic number is 3. And as you can see here, we start from electron configuration from top to bottom. So first we're going to put 1s2. Then we go to the next row, it's going to go like this. We're going to put 2s2. 2. So when you add the small numbers at the top, which are kind of like variables, it gives us 4. Then we subtract 1, so it will equal 3. So it's going to be 1s2 and 2s2 minus 1. And that's how you find the electron configuration. So non-molecular of chemical compounds. How to name ionic compounds. You first name the cation, then the anion. If named cation, then you make sure if it's only one positive charge used, then use the element name. If more than one possible charge, which are mostly transition metals, write element name including charge and Roman numerals and parentheses. Is named anion. If compound is binary, use element name and change the ending to I. If ternary, use polyatomic ion chart to name the ion. How to name covalent compounds. Covalent compounds are named by using prefixes that indicate how many atoms of each element are shown. The ending of most negatively charged elements should be changed into I. The prefixes used are mono, which means one, di, which means two, tri, which means three, tetra, which means four, penta, which means five, and hexa, which means six. Acid and bases. The three main acid and bases are Arrhenius acid bases, Bronsted-Lowry acid bases, and Lewis acid bases. Arrhenius acid is a molecule that, when dissolved in water, will donate H plus in the solution A. Common examples is hydroxide acid. Arrhenius base is the molecule that, when dissolved in water, will break down to yield an OH and negative OH or hydroxide in the solution. Such examples are sodium hydroxide. Bronsted-Lowry acid is a compound that breaks down to give a positive H in the solution. Bronsted-Lowry base refers to any atom or ion capable of accepting or bonding to a free proton, and such examples are water. Lewis acid refers to an atom or molecule that accepts an electron pair iron 3 bromide. Lewis base is an electron pair donor. Hydroxide donates its electron pair to form a bond between itself and positive H. pH versus pOH. pH and pOH denote the negative log of the concentration of hydrogen or hydroxide ions. High pH means that a solution is basic, while high pOH means that a solution is acidic. The formula for pH is pH equals negative log positive H. The symbol positive H stands for the concentration of hydrogen ion. The log of a number is the exponent that 10 must be raised to give you the number. The formula for pOH is negative log OH negative. The OH negative stands for water equals conjugate acid hydroxide equals conjugate base. Acid-base reaction is a type of chemical reaction that involves the exchange of one or more hydrogen ions, positive H, between species that may be neutral, such as water, H2O, or electrically charged, such as hydroxide, OH. SI units. The standard units in chemistry are meters, kilograms, the second, the Kelvin, ampere, the mole, and candle. Dimension analysis is a problem-solving method that any number or expression can be multiplied by 1 without changing its values. So let's say we want to find how many seconds are in 2 years. So we put seconds equals to 2 years. We know that there are 365 days in 1 year. So we put 365 over a year. Then you multiply that by, there are 24 hours in 1 day. Then, so you put the 24 hours above the 1 day. And then there are 60 minutes in 1 hour. So you put 60 minutes over an hour. And lastly, there are 60 seconds in 1 minute. So what you start to cross out, so then you have to multiply all of this, which by the end gives us 63,072,000 seconds in 2 years. If you simplify it, it's 6.3 times 10 with the power of 7 seconds. And through using this method, you were able to find the amount of seconds in 2 years. So you just basically had to multiply all the numbers, which included 2 times 365 times 24 times 60 times another 60, which gave us 63,072,000 seconds. And yeah. Now we will get into moles. A mole is a quantity of anything that has the same number of particles found in of 12.0 grams of carbon-12. That number of particles is Avogadro's number, which is roughly 6.02 times 10 over 23. How to calculate molar mass? Molar mass is calculated by finding the atomic mass of each element in the compound and multiplying it by the amount stated in the compound. Later, when you find the product for all the elements, you add it all up. Once you add everything up, that is the molar mass of the compound. So an example of this is water, which is H2O. Hydrogen contains, there are two elements of hydrogen in water, and its mass is 1.01. And when you multiply that, it gives you 2.02. Then there's oxygen. There's only one oxygen element in water, and its mass is 16. Then you multiply 1 times 16, which is 16. Then you add 2.02 plus 16, which gives us 18.02, which is the molar mass of water. Percentage composition. Percentage composition is the term used to describe the percent by mass of each element in a compound. It is typically found using the molar mass values of both the elements in the compound and the compound itself. To calculate percentage composition, you first need to calculate the molar mass, then divide the subtotal for each element by the molar mass, and lastly multiply by 100 to convert to percentage. Here, for percentage composition, we will use water as well. Like we said, for hydrogen, it was 2.02. You divide that by the molar mass of 18.02. Then you multiply by 100, which gives us 11.21%. For oxygen, its mass was 16.02, which you divide by a molar mass of 18.02. And then you multiply by 100, which gives us 88.79%. So the percentage composition of hydrogen and water is 11.21%, and the percentage composition of oxygen and water is 88.79%. And this is basically how I solved it. And yeah. And so that's all for my chemistry final video. And yeah, wear your seatbelts, guys, and be safe.